Hello. In the previous lecture, we were discussing some important results concerning Cauchy Riemann condition and analyticity of the function. In this lecture also, we are going to continue with the same theme. So in the last lecture, we have discussed that suppose f is analytic on domain D and first result we had already discussed that if fz is fz f dash z is equal to 0, it implies that f is a constant on D. F is a constant function on D. The next result that we were discussing in the last session was that if f is analytic on domain D and mod f is a constant function, mod f is a constant function, then f is also a constant function. These two results we've already discussed. The third result that I'm going to do today, suppose f is analytic on domain D and the real part of f is constant on D. Then f is a constant function on D. Okay, so let us start with this. So let us assume that real part of f is constant on D. It implies what? It implies that f, if I write it as u plus iota v, it implies that real part of f, that is u, is a constant on D. And we already know that f is analytic on domain D. It implies what? It implies that ux must be equal to vy and uy must be equal to minus of vx. And you already know that u is a constant. It implies what? Ux is equal to 0 and uy is equal to 0, which implies what? It implies that vx is equal to 0 and vy is equal to 0 by CR equations. So by Cauchy Riemann conditions or Cauchy Riemann equations, we understand that all these first order partial derivatives must be 0. Okay. If Vx and Vy is 0, it implies that V also must be a constant. And if both U and V are constant, it implies that Fz must be a constant function. Fz must be a constant function. So this is an important case. See why? Because understand one important result that I can really draw from here is, see, if I say that this constant is 0, let's say that u is equal to 0. This is also a constant function. It implies what? It implies that f would be some iota v. That is, f must be purely imaginary. F must be purely imaginary in that particular scenario. Right? And if f is purely imaginary, then what is happening? See, I've already taught that if u is a constant, then fz must be a constant function provided fz is a constant. So another thing that can be written here is that if fz is analytic plus f is purely imaginary, because in order to be purely imaginary, your u must be 0 and it must be a constant. And we already know that if u is a constant, then fz becomes a constant function provided f is analytic. So see, if f is analytic and real part of f is 0, that is, it is constant, then f must be constant. So now I'm using the same fact that if I'm placing u is equal to 0, that is a constant. It implies that f is purely imaginary. So if fz is analytic plus f is purely imaginary. So from the above discussion, it implies that fz must be constant. I'm again reiterating. See, what I wanted to tell, that if real part of f was a constant, it implies what? It implies that f would have been something like constant plus iota b, right? What if this constant becomes 0? Then also this result holds. That is, if real part of f is a constant, then f, which is c plus iota b, is a constant function. This is what it means. Okay, now what I want to convey, that if, let's say, c is equal to 0, c is equal to 0 means what? Real part of f is 0, and obviously real part of f is 0 means real part of f is a constant. F is given to be analytic, so it implies that f must be a constant function. See, if u is equal to 0, then it implies that f is only iota v, that is imaginary. So one important result I can write, that if f is analytic and f is purely imaginary, so if function is purely imaginary, it implies that real part of f must be 0, that is a constant. It implies what? F must be a constant. So this is an important result, that if fz is analytic plus f is purely imaginary, then f must be a constant function. Now see, I can extend this result again. See, I've already written this. Now this would be the fourth point that I want to mention, that if f is analytic on domain D, and imaginary part of f is a constant function. Imaginary part of f is a constant function. It implies what? It implies that f is a constant function on D. See how? Now it is given that imaginary part of f is a constant function, which implies that v must be equal to c. It implies that vx must be equal to 0 and vy must be equal to 0. So by Cauchy Riemann conditions, it is well understood that ux must be equal to 0 and uy must also be equal to 0. So it implies that both u and v are constants. Both u and v are constants. And if both u and v are constant, it implies what? It implies that fz must be a constant function. I hope you might have got it. And from here, one important result can be drawn, that if f is an analytic function and purely real function, which implies what? Which implies that imaginary part must be 0. That is, imaginary part must be a constant 0. Okay. And purely real valued, then it implies that fz must be a constant function. Okay, so this is important. Now another question, another thing I'm writing it. What if argument of f is a constant function? So if argument of f is a constant function, and obviously this is there, that if f is analytic function on domain D, and argument of f is constant, then f is a constant function on D. Then f is a constant function on D. This is an important result again. See how to prove it. So let me construct a function which is gz, which is equals to e raised to power minus iota alpha, and let's say argument of f is simply alpha and it is constant. So what I'm doing, I'm multiplying my fz with a some scalar which is a constant, because alpha is a constant here. So e power minus iota alpha is a complex scalar here. So it's a simply complex constant. I know that if multiplying with a scalar does not change the analyticity of the function. So if fz is analytic, it implies gz must be analytic. It implies what? From the algebra of analytic function, gz is also an analytic function. And what is given to us? It is given to us that argument of f is equal to alpha as a constant, which implies that tan inverse of v upon u, which is alpha, is a constant. Okay. And which implies that v must be equals to u tan alpha. Okay. I hope it is clear till now. Okay. So what are we getting now? So we've got, what is gz? Just expand it. So gz is simply cos alpha minus iota sin alpha. And then you've got something like u plus iota v. So what do you get from here? You get u cos alpha plus v sin alpha. So u cos alpha plus iota iota is fine. This is minus iota square. So this is plus v sin alpha plus, take iota common out. You get v cos alpha minus u sin alpha. And we already know what that is. V is equal to u tan alpha, which implies v cos alpha is equal to u sin alpha. Okay, so writing this and this are same thing. It implies that this goes away. It implies that gz is purely real. And gz is analytic. So gz is analytic function. And it is purely real. It implies what? It implies gz must be a constant function on D. Must be a constant function on D. If it is a constant function on D, then it implies that fz must be a constant function. See, here from this construction, you can find that fz must be a constant function. So all these results are quite important, and they may be asked in the examination. So therefore, I have written all these things in one line. Another important result I just wanted to mention was this. So I think 5 results we've mentioned. 6th result I'm mentioning now. This is again important. See, we have already discussed that fz is analytic on domain D. On domain D. And if mod f is a constant, and if mod f is constant on D, then it implies that f must be a constant function on D. So a broader statement I'm going to write here, that if, let's say, fz is analytic, fz is analytic on domain D, and mod fz is also analytic. If mod fz is also analytic, it implies f must be a constant function. So now I'm giving all the more freedom. Initially, I just took that mod f must be a constant. Now I'm saying that if mod f is also analytic, and then I'm saying that fz must be constant function. So consider a construction which is simply gz, not even construction. So I'm just redefining the function mod fz is equal to gz. So clearly, one thing is quite evident, that gz, if fz is also analytic, it implies that sorry, if mod fz is also analytic, it implies what? It implies that gz is an analytic function. Also remember, if it is mod, so what is fz mod? Fz mod would be simply root over u square plus v square. And it implies what? It implies that gz must be equal to u square plus v square, and therefore gz is a real valued function. So it implies what? It implies that gz is a real valued function and also analytic function. It implies what? It implies that gz must be a constant function. And if gz is a constant function, it implies mod fz is a constant function. And if mod fz is a constant function, fz is analytic, it implies f is a constant function. So given that fz is analytic and mod fz is constant, it implies what? It implies f must be a constant function. So what we've written that fz is analytic and not mod f is equal to constant. That is from here I'm getting. So remember, if I'm saying that mod fz is analytic, it itself implies that mod f must be a constant. If fz is analytic on domain D and mod fz is also analytic, then f must be a constant function. How did we prove? We just took gz is equal to mod fz. Gz is an analytic function which is given to us. Gz is what? Sorry. Gz is equal to mod fz, and mod fz is what? Root over u square plus v square. It implies that gz is both real valued as well as analytic. It implies that gz must be a constant function. If gz is a constant function, implies mod fz is a constant function. Fz is analytic and mod f is constant. It implies f must be a constant. So therefore, this statement hold good. So this statement is really very important statement. Okay, so all these statements are very important. They may be asked directly or indirectly in your exam. So I'm just writing them up. Okay, so this is important result. Just give me a minute. Another way of putting all these things is that if the range of f is contained in imaginary, it implies f must be a constant function. Or if I write that range of f is contained in purely imaginary, purely real, then also f must be a constant. Okay. So I'm just giving you all these variations so that you are not distracted in your exam with any of these variations. Okay. So now let us move on to another important thing. Okay. So I'm just writing it up so that you'll be able to understand. Another important result I'm going to write here, eighth number. Okay. So all these results, please keep care. These may be asked in the examination. So I'm just writing them off. See, if U and V, if U and V lie on a curve, okay, that is phi, that is U and V, I can write a functional dependence, that is phi of U and V is some constant. Okay, or I can represent, or I can, sorry, phi of U and V is equal to some constant or simply zero, I would rather say. That is, let's say if I'm saying that U and V lie on the circle, so basically it is U square plus V square equal to K square. Okay, or such and such case. So there must be some functional relationship between U and V. Okay, so whether I write it as a constant or let's say zero, if I take constant here. So if there exists some functional relationship between U and V, or other way I would write that there exists some psi, a real valued function, psi a real valued function such that u is equal to psi of v on some domain D, then fz is equal to u plus iota v is constant on this domain D, is constant on domain D. I'll let you know what I want to say. So I'm saying that if u and v are connected with some functional relationship, okay, so let's say I'm saying that let's say u and v lie on a circle, that implies that u square plus v square equal to k square, or put another way, u square plus v square minus k square equal to 0. So I'm just writing it in this fashion. Or let's say if I can represent my u as some function of v, okay, so it implies that they lie on a curve. Then fz, which is expressed as u plus iota v, this is constant on that domain D. Let us see how. See, uh, I have written um, let's say I start from here. Let's say you here, if I want to say the same thing, so u can be written as what? U square can be written simply as k square minus v square. So u can be expressed as a function of v, right? So if let's say u is expressed as some function of v, it implies what? It implies that ux would be equals to what? Psi dash v into vx. And how can I express uy? Uy can be written as psi dash v into vy. If I'm not wrong, just okay. See, also we know that uh, okay, so I'm writing, although I've written, but again I'm writing fz is analytic on domain D. So all these things I'm writing for fz being analytic only, but uh, everywhere I wrote and here I have forgotten. So it implies what? I already know that ux is equal to what? Ux is equal to simply vx, and uy is equal to simply minus vx, right? Ux is equal to vy and uy is equal to minus vx, sorry. So these are the Cauchy Riemann conditions. Okay. So I know from here that what is ux? Ux is given to be equals to psi dash v into vx. Okay. And what I can write in place of vx, I can write minus uy. So I'll write simply u of x is equal to psi dash v into, instead of vx, I'm writing negative. So negative of u of y. This is from Cauchy Riemann conditions, so just don't get worried. And the second equation, which is uy, will be equals to what? It will be equals to psi dash v. And what is vy? Vy, you know, it is ux. So I'm just writing ux here. So in place of ux, I can write this entire thing. So it implies what? It implies that ux is equals to minus of psi dash v whole square into ux. So instead of uy, I have simply written psi dash v and ux. So this is how it is. And it implies what? It implies ux into 1 plus psi dash v whole square is equal to 0. I know that this cannot be 0. It implies what? It implies ux is simply 0. In the same way, I can prove that similarly, I'm just not proving it here, but just think about it. All we have to do is simply write instead of, uh, write instead of this thing. So I'm just writing it. Similarly, one can prove that Uy is also 0. Why? See, I have proven that ux is 0. If ux is 0, I can place ux here. So uy is equal to 0. So ux and ui are both 0. It implies what? It implies that vx is equal to 0 and vy also equal to 0. It implies what? It implies that both u and v are constants. It implies what? Both u and v are constants. And if both u and v are constants, it implies what? It implies that fz must be a constant function. So all these things, all these results I'm writing at one place so that you don't get difficulty. So what bigger result we have proven? The bigger result that we have proven is that if u can be expressed as some function of v, or on the other way, if u and v lie on a curve, then and fz is an analytic on domain D, then f must be a constant function. So let us say, if using this result, if I give you one thing, let us say that if if there exists some a and b belongs to R, such that au plus bv is equal to 0, and fz, putting it here, fz, which is u plus iota v, is analytic on domain D, and if there exists a and b belongs to R such that au plus bv equal to 0, it implies what? It implies that fz must be a constant function. Why? Because here your u and v are lying on the line. Okay, so they're lying on the lying on a curve. Similarly, if there exists some a and b and c belongs to R, such that au plus bv is equal to c, then also it implies that fz must be a constant function, because here u and v are lying on a curve, or we can write that u can be expressed as some function of v, or other way around, that is v can be expressed as a function of u. So that's not a problem. Fz must be a constant function. If you remember, this case we have done, but I'm just revisiting that case for you. If u and v lie on the circle, it implies what? It implies that u square plus v square is a constant, is a constant. So u and v are lying on a circle. It implies what? U and v, u square plus v square equal to constant. It implies that fz must be a constant function. And if you remember, this particular portion we have already done. Why? See, I have already taught you that if mod fz is a constant and f is analytic, if f is analytic, f is analytic on domain D, and if mod f is a constant, then f must be a constant function. Other way of putting it, it is writing u square plus v square is a constant. Okay, similarly, if I say that if u square minus v square is a constant, what does it imply? It implies that fz must be a constant function. If u minus v is equal to constant, it again implies what? It again implies that u and v are lying on the same curve. So it implies that fz must be a constant function. So if all of these things are given to you, I don't think now you're going to get confused in any of the exams that you're facing. Okay. What if tan inverse of v upon u is a constant? It implies what? It implies that argument of f is a constant, and I have already proven that it implies that f must be a constant function. Now let us see in the light of what we have done so far. So if I say that tan inverse v upon u is constant, it implies that tan b, sorry, tan alpha is equal to v upon u, or simply v is equal to u tan alpha. So don't you see it as y is equal to mx kind of thing? So it lies on a line. So U and V lie on the lie on a straight line passing through origin. Passing through origin. It implies what? It implies fz must be a constant function. This we've already done otherwise, but now in this context, I'm writing fz must be a constant function. So all these things, all these cases are really important. So I have written all these cases at one place. Okay. So that I don't think you're now going to get confused. Okay. Now let us do a few more things, a few more results I'm going to write so that uh, you'll be able to learn more. Okay. So a few more results. Okay. So I think this will be result number 9 or something. Just help me out. I think it will be okay. So it is result number 9 that I'm writing now. Okay. So result number 9. And what this result is, just give me a minute. I'll write it once only. Okay, so this we've done. I think another result I've already given to you, so I'm not writing that up. Just give me a minute. A few important results I want to really jot down so that you don't get confused time and again. So let me write an important thing. Okay, so if I'm defining a new thing first, so if fz is a function, fz is a function defined on D. Fz is a function defined on D. And this domain is such that it is symmetric, and D is symmetric about x-axis. Okay, so when I say that D is symmetric about x-axis, what does it mean? It means, oh, so sorry. It means what? Just give me a minute. So let me just do a shape thing so that I don't know how to make a shape from here. Okay, so I can make a not only oval, I can make a circle also. Sorry. So okay, so let me just make a shape here. Okay, so what I'm going to do is see. I'm going to explain what is symmetric along. I think this is quite evident, but I mean quite clear also. But just for the sake of doing, I'm doing it so that don't get confused. Okay, so now see, if fz is a function defined on D and D is symmetric about x-axis, it implies what? That if point x comma y is there on domain D, then this point also must be there. That is x comma minus y must also be present, because symmetric about x-axis means what? That if z is present, then z bar must also be present. Okay, D symmetric about x-axis means what? D is such a domain where if z is present, then z bar must also be present, because symmetry about x-axis and makes us understand this thing. Okay, so if domain D is symmetric about x-axis, what does it mean? That if z is present, then z bar must be present, because symmetric to this point, z bar is there. I mean, if I take a symmetry or if I take an image about x-axis of z, then I get z bar. So I'm writing it here. So D symmetric means what? D is symmetric about x-axis, that is z belongs to D if and only if z bar belongs to D. So if I'm saying that D is symmetric, it implies that if z belongs to D, then z bar also must belong to D. This is what I want to say when I say that D is symmetric about x-axis. And it has been given that a function f is defined from D to C and such that D is symmetric. Then let us define a few functions. Let us say that fz is, let's say, u plus iota v. And what would be fz bar? Fz whole bar. Fz whole bar would be simply u x comma y minus iota vx comma y. What would be fz bar here? Okay. So it implies what? I'm writing u x comma minus y plus iota v x comma minus y. And what would be fz bar and whole bar? So fz bar and then again whole bar. So what does it imply? It implies I'm writing u x comma minus y and then again minus iota v x comma minus y. I hope it is clear now. Okay, so instead of z, I'm writing in the last one, instead of z, I'm writing z bar, means the points will be x minus y. Not only this, I'm also saying that I'm taking a bar over it. So again, a conjugate of it. So I hope these constructions are clear. Now we'll talk something about them. So if fz is an analytic function, on domain D, then fz bar is analytic if and only if f is a constant function. So this is like if f is a constant function. I hope this is, I think, result number 10. I think if I'm not wrong. Okay. F is a constant function. So all these results I'm writing in a place and you should be understanding them in greater understanding. Okay. So it implies what? Fz is analytic function on domain D. It implies that CR conditions must be fulfilled. That is, ux must be equal to what? Vy, and uy must be equal to what? Minus of vx. Now let us take that, let us first consider the case where fz is analytic and fz bar is also analytic. Okay, so if fz bar is analytic, so I'm just writing fz bar. What would be fz bar? Fz bar would be simply u minus iota v, right? So what should I write? I should write that here ux. So for second case, I'm writing ux must be equal to what? It must be equal to minus vy. And what would be uy? Uy must be equal to minus of vx. Instead of v, now we have minus v. So you will simply get simply vx. So this is from first, that is, if f is analytic function, then ux is equal to vy and uy must be equal to minus vx. And if fz bar is analytic, it implies ux is equals to minus vy and uy is equal to vx. Okay, because see, instead of v, we have minus v now. Okay, so just writing it so that you can get it. Fz bar is what? It is u plus iota minus v. Okay, so now the imaginary part is minus. Okay, so this is what I'm trying to explain. So ux is equal to minus of vy. So here minus of minus vy, which is sorry, ux is equal to vy. So instead of vy, we have minus of vy. Okay, because now uh, v is being replaced by minus v. Okay, so this is fine. So now by this is I think vx. Okay. Now using equation number 1 and equation number 2, what I get? I know that Vy is equal to minus Ux. So it implies that Ux must be equal to what? 0. And I know that Vx is equal to minus Uy. So it implies that Uy is equal to 0. It implies what? U must be a constant function. And not only this, if Ux and Vy are Ux and Uy are both 0, it implies that Vx and Vy are also 0. It implies that V must be a constant function. It implies that V must be a constant function. And if both U and V are constant function, it implies that Fz must be a constant function. Okay. I'm leaving the other side to for you. I think that is easy. That if f is a constant function, so if f is a constant function, so I have proven the other side. I mean, this side I have proven that if fz is an analytic function, then fz bar is analytic if and only if f is a constant function. If I take f as a constant function and fz as an analytic function, then I'm leaving it to you to prove that fz bar would be an analytic function. I think that's quite easy to see, so I'm not doing it. I think that you can do on your own because I have two more results to prove. So I hope this is something that you can do. Okay. Now, another result that I'm now claiming here is this. And what it is. So if fz is an analytic function on domain D, and fz bar is analytic function if and only if and only if fz bar is analytic. Oh, if and only if f is a constant function. See how? Just okay. So fz is an analytic function. I think this part I think you can do. F is a constant function, and if fz is analytic, then fz bar is analytic. That is not a problem at all. Okay, the only problem that you might have found was this. Therefore, I've proven one side. Another side, I think I'm leaving it to you. I think that you can do. So I'm not doing it. Okay. If there is any problem, kindly let me know. Okay. So that's not a problem. I can do it. Why it's not coming? Okay. So sorry about it. Okay. So now the result was what? If fz is analytic on domain D and fz bar is analytic if and only if f is a constant function. So mhm. See, given that f is analytic, it implies what? That if f is equal to u plus iota v, it implies that ux must be equal to what? Vy, and uy must be equal to minus Vx. Now I'm writing that if Fz bar is also analytic, it implies what? It implies that, see, Fz bar is what? First, let us write Fz bar. So Fz bar is simply Ux comma y plus iota, sorry, Ux comma minus y and iota Vx comma minus y, because now instead of z we have z bar. Okay, so now what would be Ux? Ux will be equals to v differentiate v with respect to y. So if I differentiate v with respect to y, so v would be differentiated, that is fine. And instead of y, I have minus y. So by chain rule, I'll get this. So this will be, this is equation number 1. And another part would be what? Uy is equal to minus of Vx. I think that is, uh, okay. And Uy is also negative, I think. So if I am doing Uy, so if I differentiate with respect to y, uh, so now instead of x comma y, I am having x comma minus y. So I'll get minus Uy is equal to minus of Vx. This is equation number 2. So from here, it is quite evident that that from here it is clear that Ux must be equal to 0, and from here it is clear that Uy must be equal to 0. It implies Vx is equal to 0 and Vy is equal to 0, and which implies that both u and v are constants.